Welcome, Kate Weber, Ashley Huff, and Paula Yu. Wonderful you're here today. Google Quantum AI has a significant role in this program. Virtual lab tour today, and then next week we will have Rolando Soma sharing about a recent paper on the quantum algorithm side. Kate, could you share with us what you're going to show today and introduce yourself?
Happy to. Yeah, I'll kick us off. Thanks, Marlou, and good day, morning, evening, afternoon, everybody. We are going to start off. I'll just give a brief context on Google Quantum AI's mission and roadmap, so you know where we're coming from. We'll do a short lab tour video, and then you'll hear from Paula and Ashley about kind of more in depth what happens in the Google Quantum AI Fab and Lab. So with that, and I just here's us. I lead the team's external affairs and governance. So a lot of our outreach efforts and some of our internal governance work. And then as Marlou mentioned, Paula and Ashley are both hardware engineers. Paula is a hardware engineer that helps manage our fab facility. And Ashley is one of the world's experts in cryogenics management and does a lot of work in our lab. So great people to talk about what this is all like on the ground. So this slide shows the team's mission, which is to build best-in-class quantum computing for otherwise impossible problems. And this mission is intended to capture our full stack efforts. So we are building superconducting quantum computing hardware, and also, as Marlou alluded to, developing the algorithms for these quantum computers as well. And you'll hear a lot more about the first part of that. And then you'll hear again from Rolando next week, as Marlou mentioned, which is a bit more in the second part. But for now, I'll also just show you our roadmap to give you a sense of where we are and where we're going on the team. So we have on the top here is our hardware roadmap, which we published in 2019, I believe, around the time that we announced that we'd achieved the first milestone on this roadmap. You see it has 6 hardware milestones, the first of which is this beyond classical benchmark, which at the time we called quantum supremacy. We've moved away from that term, but I mention it just so people kind of can match this milestone to the announcement at the time. And that was showing that for this random circuit sampling algorithm, our quantum processor, Sycamore, would outperform the fastest, most powerful supercomputer at the time. It took about 200 seconds on Sycamore and would have taken 10,000 years on that classical supercomputer. Of course, both classical supercomputers and quantum computers have evolved since then, and the classical algorithms community has also been working on speeding up this random circuit sampling on classical computers. However, we will shortly announce an update to this result showing that indeed quantum computers do retain this beyond classical advantage, and we are seeing the kind of double exponential progress that we expect as quantum computers improve. So we announced our second milestone last year that was the logical qubit prototype, essentially a proof of principle of error correction, showing that we could use quantum error correction to reduce errors in a calculation, even as we increased the number of qubits used for that. And we're now working toward a long-lived logical qubit, so a logical qubit with an error rate of 10 to the minus 6th. And then from there, you can see we scale up towards this error-corrected quantum computer, which we expect to have around 1 million physical qubits. So lots of work to improve the qubit quality, the error correction, and also that scaling up is a really big challenge, which I think both Ashley and Paula can attest to. And then on the bottom, just briefly, this is our business roadmap. It's in pink. We are a bit different from some of the other quantum computing providers in that we are very focused at this point on improving our hardware and making progress on this quantum computing hardware roadmap. And our plan is to offer commercial access only once we have a quantum processor capable of commercial applications that you would not be able to run on a classical computer. And with that, I'm going to go ahead and play this short virtual lab tour video, and then I will turn it over to Paula.
Hi everyone, my name is Eric Lucero. I'm pleased to have you here at the Quantum AI campus. I'm going to walk you around, show you a bit about not only the history of how we got here, show you a little bit more about the space and the lab and where we're headed. So I'd love to start with our Sycamore quantum processors. Behind this piece of metal right here, on this circuit board and all these connectors that we have, is the actual quantum processor. This system gets mounted into our cryostat, and that system we're going to see in full scale in just a moment inside the lab. So it's also a pleasure to have you here for all the reasons we can show some of the collaborations that we've had from our 9-qubit systems that have now scaled up to, say, beyond 54. Here's a nice example of one of our systems that we had that was 22 qubits. And it's really cool because all these will be put together in the lab that you're about to see. So I'm going to take you there. So come with me. Now I'm going to show you where we take those Sycamore processors that I showed you earlier and install them into the cryostat. So we're going to walk over to one of my favorite systems here. This little cryostat is what we use to cool those systems down to really a couple orders of magnitude colder than space. Basically, each one of these metal stages that you see here, from this edge all the way down, kind of in this layer cake, the very bottom of that is what we call the mixing chamber. At that point there is where we mount the quantum processor, that Sycamore system that I showed you earlier, and it thermalizes to that plate. That plate gets to 10 millikelvin. That's really cold. That's some of the coldest places in the universe. That's 2 orders of magnitude colder than, like, between 2 galaxies. All of that system runs all the way up the top where we have wires that come out. You can see over here on our control system, those are custom control electronics that our team, engineers here at Google, have done and designed specifically to control the quantum processor inside. I like to think of them as a music player, playing music to the qubits. There's some analog pulses that come down, and that musical score gets played through those wires all the way down to those qubits. There's a lot of different skill sets all over the world that these people are coming from to join the team and think about what is a quantum computer actually going to serve everyone, and how do we do that responsibly for the world and make this a tool for humanity. All right, so now I'm going to tell you a little bit more about what this space is going to look like as we scale in the future. Today, we are here right now at this point where we've just gotten past the beyond classical experiment. And we're headed towards these next milestones to build an error-corrected logical qubit, and finally, to an error-corrected quantum computer. Now, this space will grow, and we've really designed it to be the kind of place where we can land a number of these milestones along the way. Each one of these cryostats are systems that our team has spent many, many hours in design and customizations to make these some of the most powerful quantum computers in the world. We can do the impossible. And we look at quantum computing, something that we look at as maybe it's a 10-year investment. At the other end of that will be this tool for humanity. And I think it's an important part of that style of creativity that is not just a scientist's creativity or just an artist. It's actually kind of that combination of both that gives us the ability to be inventing the future. So it's been a pleasure to share with you all this space. I can't wait to show it to you in person and to see this place come together for an error-corrected logical qubit. Until then, take care. I'll see you all later.
Great. So I'm going to turn it over to Paula next to talk about how we make these processors.
Thank you, Kate. Yes. Hello, everybody. I'm Paula Hugh, and as Kate mentioned, I work here at Google in the fabrication lab. So essentially, all the clean rooms that is where all of this takes place. In front of you here, you see a sample of what a qubit kind of looks like, and you can kind of see that they're super small. Our features are in the submicrons in some cases. So it is actually very difficult to visibly see them, even under the microscope. It is very difficult. As I mentioned, all of this is done in a clean room using fabrication tools, and they're all processed with a very awesome group of fabrication techs who do this day in and day out. And so the method that we use and the tools, the whole process, everything, every part of that is very critical. Okay, you can go on to the next slide. So this is kind of what a completed device looks like. You can see on that chip, it's a whole chip, but on that chip has many qubits. So let's talk about just qubits first. What is a qubit, right? So a qubit is basically a quantum information or unit. It is super sensitive. and which is part of the reason why we have to cool it down to such cold temperatures. On this chip, there is a detector side of it, and that's the top part. The detector itself, which has a qubit, is basically an inductor and a capacitor, and that's actually etched into an aluminum-coated silicon wafer. So this is a basic fabrication processing with aluminum and silicon wafers in a fab. But how is the qubit made? Well, they're actually, like I said, similar to any other chip that you would fabricate. Many of you have phones, and inside your phone, there's a lot of chips. A lot of those chips are also fabricated in a clean room. So very similar type of fabrication tools and processing. And they all use basically common superconducting materials like aluminum and silicon. So those are the two pure metals and materials that make up the qubit themselves, basically. So what does it look like? So this is what this picture is here about. A qubit, basically, you'll see we use what you call a Josephine junction, or in short, JJ, if I refer to a JJ. And that's basically just two metal legs on top of each other with the insulator between them. And they cross, as you can see there, at 90 degrees angle. And that's kind of what creates that capacitance between them, because with the two plates you have on them, and it just looks like a shape or a cross, so you can look at it that way. But that is kind of how we measure the state of the qubit at any moment in time. So JJs are very difficult to explain sometimes, but if you just think of it as like a tuning fork, it could turn in any direction, and at any point in that direction, it has a state. And that's what we're trying to measure. And so you can kind of think of it as it's an oscillating part, and it's oscillating at very high frequency. And you add power to make it oscillate, but that's kind of a state that we will measure at any given point in time. And unlike traditional computers, it's not just two states, not a 0-1, but it could be multiple states. And that's what makes this super difficult to manufacture, test, and produce. Let's go ahead on to the next. Let me finish off this slide here really quick. So you'll see the bottom picture is the top. It's a qubit side, and then we have our circuit board or control board, and those two get hybridized together. When we say hybridized, we're basically taking them, aligning them on top of each other, and then they're connected through bumps. So what the bump is, what is made out of indium, and you can kind of think of it as like an Oreo sandwich. So your bump is kind of filling inside, but they're all very particularly patterned so that they would line on top of each other. And just think of it as two interconnects that is taking a signal from one chip and transferring it to the bottom chip, which then gets connected up to a whole bunch of electronics. And so we'll go over that part a little bit later. But and essentially, just think of it as you always have to have two sides to it. One's kind of your readout circuit board side. The other is your chip or qubit side. So without one or the other, they doesn't actually work. So that's one of the difficulties of making this chip, is that you've got to make two different sides and they get hybridized together. So let's go on to the next slide. Packing qubits. Yes, okay. So when we say packing qubits, it means that the chip now has been hybridized so that it is all one chip, and now we need to put it into a package. So just think of it as we have to cool this down. And if you kind of think of if you get a cold drink out and you leave it on a table, as it warms up, the humidity kind of starts to condense on your can, on the outside of your can. So the same thing would happen to our chips, which is the reason why we package them. So packaging essentially is putting this chip into a closed unit and sealing it off so that no air can get in it. It's kind of in its own environment so that when we do cool it down, it stays dry and will operate as expected. These only operate at very, very, very cold temperatures, so 10 to 20 millikelvins, which is just super cold, which is why we need these gigantic, huge systems to house them while we're testing them. And then all of this gets what we call wire bonding out. Just think of it as a wire, but these wires that we are using are like 1/4 of a human hair, and that actually connects our control board to external electronics. And those electronics connect to more external equipment and electronics. And so that's how we end up with this massive system. And that is just all to keep the devices cold so that we can actually read the state of each of the qubits. All right, and I think that is the end of mine, so I'll hand it over to Ashley.
Thank you, Paula. As Kate and Marlou mentioned earlier, my name is Ashley Huff, and I am one of the cryogenic engineers here with Google. Basically, to sum up my job, it is to make things very cold. And as you see in the picture, you have the traditional chandelier that's shown in all the pictures. And this is the inside of what the dilution refrigerator looks like. So you'll see it's a series of different plates. And you can kind of think of it as like a Russian nesting doll, if you will. Each plate gets a little bit smaller and a little bit colder. So at the top, you see the two aluminum silver colored plates. The upper one, the biggest one, stainless, is 300 Kelvin. Then you move down to the first aluminum plate and you're at 50K, 10K. Then the first gold plate you see is 3 Kelvin. The second gold plate is about a Kelvin. Then you take a step down in order of magnitude again. You'll go down to about 0.1. And as mentioned in the video, the bottom plate is about 10 millikelvin. For those of you who like Fahrenheit, that's about minus 450 degrees Fahrenheit. So when we say cold, it's cold. Now, why do we need it this cold, really? So as the name kind of gives it away, we do superconducting qubits. And for most of you, superconducting cannot be done at room temperature, so we have to go cold. But still, most of these materials go superconducting about 1 Kelvin. So why do we need 10 millikelvin? So to go below the noise threshold and to make these qubits as quiet and as easy to read as possible, we need them to be as cold as possible. Hence the dilution fridge. And inside of the fridge, we also put in all of these wires. And these wires are used to not only read out, but control the qubit. Then on the left-hand side, I think, the picture with the person in it, all of those wires that you see inside of the fridge go to breakout panels on top. And those all run to our custom electronics. And those are what we use to send the signals and actually talk to the qubit, like Eric mentioned in the video. So I think next slide. And then talking to the qubits, right? So building all of this hardware is great, but now you need to do something with it. So this is where we use these electronics to send a series of different pulses and gates to the qubits. And these allow us to control the qubit from either the 1 state to the 0 state or the other way around. Some of the lines are used to read out so we can actually figure out what the signals are. So there's a lot of wires to do, to do some very simple, well, not simple, to do different gates that allow us to control the qubit and to do all of these really complicated calculations. And next slide. And I think that is the end of my portion.
Yep, I think we're ready for Q&A. This is just one more photo of our lab. Eric kind of mentioned in the video, but we have artists in residence, so it's kind of a cool space. And then a photo of the team that makes this possible. And with that, sounds like there are some questions.
Wonderful. Thank you, Kate. Thank you, Paula. Thank you, Ashley. This was a great lab tour and great presentations. Also really making clear what that chip looks like, what the dilution refrigerator looks like. I am tagging or spotlighting my colleagues as well. My colleague Miriam Bautista from Lawrence Berkeley National Lab is joining. My colleague Jasmine will join soon. And then we will start the Q&A. To kick it off, we are very curious about your background. Kate, you're the head of governance and external affairs at Google. Can you share more about your role? And then after that, Paula and Ashley, about your trajectory into quantum and your roles as quantum hardware engineers. And then there are already many questions also about what you just shared. We're excited to enter the Q&A. Go ahead, Kate.
Good. I can start. Yeah, I actually I have a background in molecular biology. I did a PhD, and then after that decided I didn't want to work in a lab anymore. I moved to Washington, D.C. I did a couple of science policy fellowships, ended up working at the Department of State for about 5 years, and became essentially very interested in this intersection between the scientific research and societal implications. And so when I left the government, was interested in another role in that space, happened to be living in the Bay Area at the time, and this really interesting role working with Google Research on Google's government affairs team came up. And so that's how I ended up joining Google. So I've worked with Google Quantum AI since the beginning of my time at Google, almost exactly 5 years ago. And about 1 year ago, I joined the team full time as the team grows and also government interest in this technology grows. There was more scope for that kind of work in the quantum computing space. So I'm now doing that sort of interfacing between the team and the government, but also with other sorts of stakeholders. So academics, industry, managing our relationships and external partnerships, and also just kind of the way we frame our work to non-technical external audiences in particular. And then I do some work on internal governance, setting up processes for operations as well. So that's me. Maybe, I don't know, Paula, do you want to go next?
Sure. Yeah, so my background is actually in manufacturing many types of semiconductor devices. The very first device that I actually worked on was the rewrite heads that went into every computer. So that little magnetic head that reads the 0 and 1 bits. So I feel like I kind of almost come full circle here, because now we're going into qubits versus these traditional rewrite heads. But yeah, so that's where I started, and I was always very interested in fabrication and semiconductor. I actually got a lot of my formal training in biology and then switched over to information technology because I was always very interested in technology. But continued to work in the fabrication side, specifically in clean rooms, because that's kind of where all of the nitty-gritty stuff gets made. And it's also a very important aspect of all the chips and future semiconductor processes. But yeah, I started there as an engineer doing a lot of process development. So rewrite head, as I mentioned, was one of them. I've worked on super mirrors. I'm not sure if anybody knows what super mirrors are. They're Bragg mirrors. I've worked on infrared detectors, LEDs, many other type of semiconductor devices, I guess you could say. So, but anyways, I've been over at UCSB, so I've been doing a lot of development work for companies out of UCSB, and I also started working with Google probably, I want to say, maybe roughly 7 years ago, not as an employee, but as a collaborator from other companies. And we were just working on sharing technologies, and that's kind of how I got introduced to the Google folks. And then I joined later on when they were ready to bring up their fabrication labs. And so I am here now running the clean room fabrication lab all the way to the packaging clean room lab. And so my team basically is essentially responsible for making all the devices that then get packaged and cooled, and then it goes. So Ashley works on the test side of it, and I work on basically the front side of it, making sure the package is ready to be cooled down.
Fantastic to hear that both you, Kate, and Paula actually come from another field and now use all the skills you acquired there in the quantum field, where we need so many people with many different backgrounds. How was that for you, Ashley?
So I have a background I have a bachelor's in physics. When I was doing my undergraduate, I worked as a student researcher in a lab on CDMS, the cryogenic dark matter search. So my job was pretty much to install detectors in a DR, cool them down, test them. So I spent a lot of time servicing and running a DR. And when I graduated, I really didn't feel like going to grad school. And I saw Janus, the company whose DR I was running, was hiring. And I figured if I can run one and I can fix one, how hard can building one be? So I joined Janus, and then I spent about 9 years there designing, building, and installing fridges. I actually built and installed the majority of Google's fridges, which is how I kind of got involved with Google. And then about 3 years ago, I left Janus and joined Google full-time as one of their cryogenic engineers.
And Ashley, since you're an expert on getting things cold, there are 2 questions related to that. Rebecca asks, could you talk a bit more on how the temperatures go down, plate by plate? And then Kevin asks, are there any difficulties with materials behaving unexpectedly at such low temperatures?
Sure. So inside of a dilution refrigerator, there's 2 main cooling circuits. The first one is the pulse tube, which if you've ever been in a lab that has one, it's the wonderful noise that just runs 24/7. So that is cooled, that is linked through copper braids to the top 3 plates, the 50K, the 10K, and the 3K. And these are dual stage pulse tubes. They're standard products that you can buy. And the upper stage gets to 50 Kelvin. The second stage of the pulse tube gets to 3. And we clamp in the middle, and that gets us a 10K plate. So using just an off-the-shelf item, we're able to get down to about 2 Kelvin. So then once we get to 2K is where the second cooling part of the dilution takes over, which is the dilution core. So the DR core is linked to the bottom 3 plates, which are the still, the ICP, and the mixing chamber. And so inside of there, we have a mixture of helium-3 and helium-4 gases that you then liquefy inside of this fridge. Once they get very cold, some strange quantum effects start to happen, and you actually have what's known as phase separation. So the helium-3 and helium-4 will physically separate like oil and water and sit on top of each other. And then you pump on it, some other fun stuff happens. If you want to know more about it, Pavel is like the greatest book ever on cryogenics, and he will walk you through all the physics of how the DR works. And so that's then how we're able to get to 10 millikelvin. And then as for materials, yes, you have to be very careful about what materials you use here, because we're talking at the mixing chamber, the cooling power for these fridges is measured in microwatts. So you have to be sure that you don't have very strong thermal links, but you still need electrical noise going through. So material properties and selections inside of a fridge is very, very important. And it makes, finding material for these sometimes very tricky, because what works is a great like aluminum, which is great for the upper plates. It goes superconducting, so we can't use it for the lower plates. But, copper's great, but it's also highly thermally conductive, so you can't have it as a link between things. What you put as, So it's a very complicated material selection process, which Pavel also goes through.
Very clear. Kate, you said the Google quantum computer will be available once it is basically ready for a quantum advantage. Are there opportunities in the meantime to collaborate, or for these research fellows who are diving into topics, fundamentals, chip design, but also applications?
We do a lot of collaborations, on this algorithms theory side. We also have a couple of external users of our hardware. Those are really focused on groups that have interesting ideas for groundbreaking algorithms that we can run on today's hardware. So it's more of a kind of mutual collaboration model versus a commercial one at this point. But definitely, if you have specific ideas, reach out to us, and happy to explore it there. We also have opportunities for like students. Google has a student researcher program, and we have a number of quantum computing student researchers every year, including, and we also have a program for kind of hardware fellows. So there are definitely opportunities to work with us in the meantime before we get to this commercial stage, but it's much more of an R&D focused effort at this point.
And that brings us already to the end of this session. I would like to thank Kate Weber, Head of Governance and External Affairs at Google Quantum AI, Paula Yu, Quantum Hardware Engineer on the fabrication side at Google Quantum AI, and Ashley Huff, Quantum Hardware Engineer on cryogenics at Google Quantum AI. Thank you all for this wonderful session with virtual lab tour presentations and extensive Q&A.